Testing, testing, 1, 2, 3. All right. Okay, recording is working. Whew. I just made it.
With the exception of Ms. Bellier and Mr. Zazari's class, that would be great.
Okay, now let's see. I need one note.
It's Bellier, Laser, Cardamon, Colbert, Kushwick, Kwan, Liang, Liao, Moreno, Ned, Overas, Rolfe, Bryant, Samble, Sin, Vandides, Weinberg, Zazari. Thank you.
Okay, view, tabs, layout. Where's the thing? View. View full page? Oh no, don't want that. Ooh. Actually, that's not bad. Huh? No, some people are still coming back. Because those people are here. Yeah. And here. So we'll start in a moment. That's so exciting. Okay. Oh no. Okay. More notebooks. This will take me a second. I just got to open a notebook here. Okay. Super fun. We'll see where the heck this thing is. Class notebooks. Let's try that one. Nope, not that one. Notebooks. Yay. Okay, here we go. There we go. Open. Okay. Hooray! Okay. Why is this not? Okay, and we want solubility 2. Hooray! And we want 3.2. I think we finished 3.2b. Yeah, we did. We are on page 36. Phew. Okay. Let's hope this pen works. Yay, it does. Okay, page 36. No, what happened? Where'd you go? No, Okay. There we go. Okay. Yes? Do I have pencils? I can lend you a pencil, yes.
Because I left one of my...
This is a twist over.
Where do you get these from?
Staples. And it doesn't break very easily because it's springy. But you don't want that much lead out at a time. Otherwise it will break. All right. So we are looking at this equilibrium here. We have calcium hydroxide, which dissolves into calcium and hydroxide, shockingly. Let's see if this is better here. Can I get my pens? No, I cannot get my pens. I don't know what the heck. That's okay. Making do. There we go. All right. How could we make this more soluble? We could heat it. Yes, we could add some temperature. We could increase the temperature. So we need to shift this equilibrium to the right. Why does it look like this? This is irritating. Let's try that. See if that works better. We're going to shift it to the right. That means we're going to be dissolving more solute. Oh, hang on. Okay, there we are. Okay, I might just have a mental breakdown, but that's okay. Okay. Why are you jumping? Jumping. No jumping. Stop jumping. Okay, no, it's taking my writing and turning it into text. That is not what we want. Let's see what else we got. Let's try this one. Okay. Or maybe, yeah, let's try that one. Okay. Apologies. I don't know. It's just stupid. Pen. Thickness. Let's make it red, because at least that'll show up. Okay, maybe that's going to work. We'll keep our fingers crossed. It's going to go to the right. Okay, right. Let's see if that works. More solid. Okay, more solid solute. Most solid solutes become more solid, more soluble when we increase the temperature. That means if they become more soluble, the dissolving process, would it be endo or exothermic? It would be endothermic. Yes, indeed. Okay. Calcium hydroxide is a typical solute in that it becomes more soluble as temperature increases. There are occasionally solutes that become less soluble as temperature increases, but they are very rare, and I don't know of any examples offhand. Okay? So that means that we must have our heat term must be over here. Yes? Okay. To decrease the solubility of the calcium hydroxide, what would you do to the temperature? Decrease. Which would shift the equilibrium to the left. That would mean, is there more or less calcium hydroxide dissolved? There is less, and the ion concentrations are lower. So what has happened to our solubility in this case when we decrease the temperature? We have, when we decrease the temperature, what have we done to the solubility? Yeah. Where are my more commands? Favorite pens? No? Okay, never mind. Trying to make things better, but it's not working, so we'll just keep going like this. All right. There we go. What effect would increasing temperature have on the value of KSP? It would increase. KSP. Okay, so increasing temperature, what does it do generally to the solubility of most salts? It increases the solubility of most salts. Decreasing temperature does what? Decreases the solubility of most salts. Okay. Now, how else, actually, before we do that, CaOH2, Ca2 plus 2OH minus. What is another way that we could get that equilibrium to shift to the right? Sorry? Add more CaOH2. Let's try that. Remember, this is a solid. That is aqueous, and that is aqueous. And right now, because we are at equilibrium, yeah, exactly, huh? Okay. I'm not going to try highlighting anything anymore. I'm just going to... there we go. All right. How else to get the equilibrium to shift to the right? If we add more solid... Oh, since we are already at equilibrium... What does that tell us about the solution? It is saturated. So if we add more solid, what happens? Nothing happens. So how else would we get this equilibrium to shift to the right? We could decrease the concentration of the ions. Would that work? Yeah? So if we could get either one of these to go down, that would work. I want you to think, what could decrease those ions? You can add an acid and that will react with the OH minus. Absolutely. Okay, so now we're kind of ready to go on to the next page. Sort of, I think. Okay, there we are. Anything that increases the solubility will shift the equilibrium to the right. Anything that decreases the solubility will shift the equilibrium to the left. And so we could add an acid. What will an acid do? Yeah. H plus reacts with OH minus, giving us water. And therefore, what happens to our concentration of OH? Concentration of OH decreases. And therefore, the equilibrium shifts right. Can you think of something we could add to decrease the calcium concentration? Maybe add an anion. What anion would be a good one? SO4 2-, yes, because if we add SO4 2-,
Should we add something that has SO4 but like the cation doesn't precipitate with the...
yeah, so we would add, what would we add with our SO4 2-? We could add Na2SO4, and the SO4 would precipitate the calcium, and that would shift it to the left, which would, or sorry, the right, yes, which would increase the solubility. What if you wanted to decrease the solubility? What could you add? You could add base, yeah, potassium hydroxide, sodium hydroxide, because that would cause the, so if we add a base, the concentration of hydroxide will increase, therefore it will shift left, and it becomes less soluble. All right, let's try a few examples here. What is the effect of each of these on the solubility of calcium hydroxide? What if we add calcium nitrate? Everybody. What will happen to our solubility if we add calcium and nitrate? It will decrease because we're increasing the concentration of calcium. It will shift to the left, and that will cause the solubility to decrease. Shifts left, solubility decreases. What happens to KSP? Chat about that. So here's a concentration diagram. Yes? So we added some calcium. What happens to the calcium now? Goes down, doesn't quite get to its original level. What happens to our hydroxide? Goes down by twice as much, but there we are. But both of them, like this one's higher than before, this one is lower than before, but the ratio remains the same. I know it doesn't look like it because I've drawn the diagram badly, but
Oh, so they both decrease the X.
this would be like a 2. But what'll happen is that they will both end up at a level where KSP is the same, because that's the whole point of K. Why would we call it a constant if it changed every time you did anything to it? What's the only thing that can change a K? Temperature. If it changed when we changed concentration, it would not be a constant. It would be a variable. Yes? The only thing that can change a K is temperature. So KSP stays the same. Only thing that changes a K is temperature.
So in KSP, this makes it equal to the constant CA plus
Yep.
times constant which minus square.
Yes.
They both decrease.
Calcium's higher than it was before,
Oh,
right? I mean, we can do the math if you would like. Or do you want to just believe me? We can do the math, sure. Okay. So we have Ca 2 plus, let's see, CaOH2. Can someone go find me? Oh no, we can't, because let's not do calcium hydroxide because we don't have a KSP value for it on our table. Let's find one that we do have a KSP value for. We have a KSP for magnesium hydroxide, 5.6 times 10 to the negative 12. Okay, so we have now, we would like to find the solubility of MgOH2 at 25 degrees Celsius. And we know that the KSP is 5.6 times 10 to the negative 12. Solubility is measured in, it's the amount that can dissolve in a given volume. So it is in moles per liter. So what we are looking for is if we're looking for the solubility of magnesium hydroxide, what we're really looking for is the concentration of MgOH2 of a saturated solution. Yes? Okay. So we know that, let's let the equal the concentration of MgOH2 saturated. Yes? In that case, this concentration is X. Yes? You with me so far? Okay. And for every one of those, how many mg's do we get? 1. So that's X. I'm going to put this in brackets because this is a solid, right?
I thought, how much concentration for this solid?
Okay, so if I dissolve a mole of 1 mole of NaCl in a liter. What do I say the concentration of NaCl is? I say it's 1 molar NaCl. Do I have any NaCl? No. Does that stop me from calling it 1 molar NaCl? No. We good? Okay. So some amount is dissolved, that's X. What are our ion concentrations? We're going to have X and we're going to have 2X. All right. So now we have our KSP. I'm sorry, everything is the same color. It makes it really hard to see, but changing pens apparently is too hard. I'm going to have to learn how to do that over lunchtime. So we have KSP is equal to concentration of Mg 2 plus times OH minus squared. And so we're going to have then that is equal to X times 2X squared. Okay, so that's going to then be 4X cubed, and KSP is equal to 5.6 times 10 to the minus 12. So X cubed then is equal to, calculator, where are you? There you are. 1.4 times 10 to the negative 12. And we're going to take the cube root of that. Do I have a cube root button? I do, thank goodness. 1.119 times 10 to the negative 4. Okay, and so that is equal to 1.119 times 10 to the negative 4. So I'm just going to call that 1 times 10 to the negative 4 to make life easy for us. Are you okay with that? I'm just going to call it 1 times 10 to the negative 4 because we don't care about sig figs. We're just trying to prove a point. Yes? Okay. Now what we have is we have Mg OH2 and we have Mg 2 plus and we have 2 OH minus, and right this moment we are at an equilibrium state, yes? And so this is 1 times 10 to the negative 4, and this is 2 times 10 to the negative 4. And now what we're going to do is we're going to add some magnesium. Yes? So we are going to add 0.1 molar magnesium. Okay? So this is our initial, because we're now messing with our equilibrium. We're now no longer going to be at equilibrium. Okay? So this is going to be 0.1001. Yes? And this is going to be, or sorry, yeah, that's right. And this is going to be 2 times 10 to the negative 4. All right, and now we're going to have a change, and we're going to have equilibrium. So these are going to, now which way is it going to shift? We increased the concentration of Mg. It's going to shift to the left, which means these are both going to go down. They're going to go down by, let's call it not X this time, let's call it Y. Okay, just because otherwise we've got 2 X's and that looks a little confusing, right? Okay, so we now have 0.1001 minus Y, and we have 2 times 10 to the minus 4 minus Y. 2Y, thank you. 2Y. Excellent. And now what we have to do is now we have to say, okay, my KSP is equal to magnesium squared, or sorry, magnesium 2 plus times OH minus squared. And then that's going to equal, what does KSP equal? 1 times 10 to the negative, or sorry, 5.6 times 10 to the negative 12. Yeah? And then this is going to be, you know what? To make life really easy, what I'm going to do is I'm just going to say let's assume y is insignificant. Okay? So this is going to be 0.1001, and then this is going to be, you know what? I'm just going to call this x, because 2 times 10 to the negative 4 is really small, right? I just don't know what this number is here, right? But I do know what this number is. So do I need to actually solve for what the change is, or can I just solve for the equilibrium concentration and call that, I don't know, Z? Can I just call that Z? Is that not okay? Okay, but I know what, and this is so frustrating to me because I can't highlight things. Okay, we know what that number is, yes?
Yes.
If I say let 2 times 10 to the 4 minus 2y equals Z, is that okay? Okay? Let this equal Z. So I'm just going to call that Z, because that's going to make my math easier, yes? Now I don't have to do a quadratic, right? Okay, so now what I've got is I have 5.6 times 10 to the negative 12, 5.6 times 10 to the negative 12, are you regretting asking this question? Divided by 0.1001 equals, and I get 5.6 times 10 to the negative 11 is equal to Z squared. And so Z then is equal to the square root of that, which is 7.5 times 10 to the negative 6. So that is the concentration of hydroxide at the new equilibrium. Yeah? So what happened? I went from 2 things that had 10 to the negative 4, right? That was my initial equilibrium. Now I have one thing that is at 0.1, and I have hydroxide, which has gone down to 0.6, but that's squared.
Oh, so basically like what happens is that when you increase the CH plus,
Yep.
the CH plus like one increases, and then as the reaction proceeds to the left, the OH minus doesn't go down, so the SB stays the same.
That's correct. Yep. Now, are you going to have to be able to do this math? No. Okay, that's kind of crazy. But, did you kind of follow along? Okay, cool. All right, so we were over here, and we were saying if we add calcium nitrate, it shifts left and the solubility decreases. What if we add NaOH, sodium hydroxide? It's going to shift left. And the solubility decreases. What happens to KSP? KSP stays the same. What if we add some sodium chloride? Nothing happens. Why not? Does sodium do anything with either of those ions? No. Does chloride do anything with either of those ions? No. So you will have no shift. Same solubility as water. What about adding HCl?
But doesn't adding salt makes this it's more thick now. So it is like it's only for one species, right? So like adding
Doesn't quite make sense to me either, but there we are. That's life. That's how it works. Okay? Yeah. Now what if we add HCl? It's going to shift to the right. Right. Why is it shifting to the right? The hydrogen neutralizes the OH, absolutely. Okay, so we have H plus and we have Cl minus. Our H plus comes in here, it grabs the hydroxide and we get water. So this causes the concentration of hydroxide to decrease, which causes a shift to the right. So the solubility increases, and what happens to the KSP? Stays the same. KSP stays the same. What if we add Na2SO4? Yes. Ca2 plus reacts with SO4 2 minus to form a precipitate CaSO4 solid. Those are aqueous. And remember, this is a precipitation equation, right? So we'd use the one-way arrow, yes? And so therefore, the concentration of calcium does what? Decreases. And therefore, we get a shift to the right. Yep. So if we decrease this, that shifts to the right. And if it shifts to the right, solubility increases or decreases? Increases. And KSP stays the same. Now, we're going to take, before we flip the page or do anything exciting like that, actually, no, I guess we're going to fill this in first. If you decrease concentration of an ion in a solubility equilibrium, is the solubility going to increase or decrease? It's going to increase. If you increase the concentration of an ion in a solubility equilibrium, the solubility will decrease. Now, this particular one where we, yes?
Are we supposed to have a break?
At some point, yes. When is class over? Let's figure out. Class is over at 12:05. You guys want to take a break now? Sure. Okay, so we'll come back at 20 after. Okay? Yeah. And maybe I'll learn how to use this pen. There were some words going in front of pen in my head. Choose what my shortcut button does.
Get us locked up there, bro. What are you doing? No, come on. No, come back, bro.
Oh. We have a break right now. Till 20 after. So 10 more minutes. Oh my dear God. Okay. Choose what my shortcut button does. Yes?
For example, let's say this 1 molar is
Yeah.
saturated.
Yeah.
So that's like 1 molar,
Yeah.
molar and 2 molar. But what if we have like 100 molar of CaOH2 that's absolutely saturated? Is it also 100 molar and 200 molar? Oh, so it's like
Whatever
all-
the saturation is, these are proportional
because
to
I
that.
thought the ratio is only for the consumption of the CaOH2.
But that's what a saturated solution is.
Also, it's like all of the
All of it.
CaOH2 take part in the
Yeah, there will be there can be solid left over,
yeah.
but that's how much dissolves.
Oh, I see. Okay.
Yeah.
Okay, thank you.
Okay, cool. I don't understand this.
Like, LeChalier's is not really soluble. That's a really good question. Is that
Yes.
if like some active bases is not really soluble, is it still considered to be electrolyte?
Um.
Because in 3.1 it says like all ionic compounds, acids and bases are electrolytes, but it doesn't mention weak acid or like
Yeah, weak bases.
Good morning. We are now ready to start sending students down to the gym for the third and final assembly. I'm going to read the list of teacher names. Would the following teachers please bring their students in through the upper entrance? Everybody else will enter through the lower entrance by the gym. Teachers coming in through the upper entrance are Mr. H, Miss Singh, Miss Spence, and Miss Wu. The full list
We
of teachers
switched.
going to this assembly: Albrino, Burtness, Verderer, Costa, Dardano, Donati, Gatti, Mr. H, Kim, Kimishida, Lamb, Lucken, Osinas, Panesar, Riley, Richardson, Sastry, Singh, Siverson, Spence, Stewart, Evangelista, Brand, Welsh, and Wu.
What?
Thank you.
I don't know what they're doing. All I know is we've already been, so we're not worried about it. Anyway, yeah. It's just saying that they are electrolytes, so it's not saying whether they're strong or weak. Right? They have ions. They might be weak electrolytes. Yeah.
But they are.
Yeah. But yeah, it doesn't specify whether they're strong or weak. I think that comes later. Yes?
yeah, it's not in the first.
No, it's not in there, and we might even not deal with that until acids and bases, which we've already done though, so you're ahead of the game. Yes? Yes.
So basis here is as page 3.
And then you'll put it in one.
So it is that.
Yeah.
Oh, okay. Okay, that means it could be all factors. So 10 minus 7 So this is like I know like an X, yeah. Okay, but like so this is 10x squared.
Yes?
Do you have any suggestions on like what else I can like do for review or to practice or
For what?
for the quiz or the test or to just understand this? Because I don't know. I'm doing so much review and I try to understand it, but it's
I would just
Okay, but there's not much to understand, which is maybe why you're having trouble trying to figure out what you need to understand. Because you just need to understand that
Key concept.
the things separate
Yes.
if they're ionic or if they're acids. If they're molecular, they stay together. Yes? And all you need to do is be able to write net ionic, complete ionic, formula, net ionic, and complete ionic equations. What is there to understand? Like, there's nothing to understand. You know it already. Yes? I think the only thing that's new that wasn't like part of grade 11 is qualitative analysis, which is where you have to add an ion to precipitate this one. And for those ones, I would just practice, right? And there's lots of practice in there, and if you need more practice, there's more practice in Hebden. I think it references some Hebden practice as well. Yeah? And I need to see if I can make my pen work, so I'll be back with you in just a second. Okay. What is wrong with this effing thing? More commands. Modify tool. Yes. Okay. Modify tool.
Electrolyte is ionic. Well, they have it anyway. It says electrolytes always start with natural charge force. Or it's like acid. CO is also acid. So basically acid and ionic.
This is so funny. I have two sides.
Natural.
I'm like, oh, it's already.
Oh no, no, no. No, no, no.
I think more than one person wanted. Is that a circuit? That's a circuit.
I think I'll leave one
It's crazy.
Oh my god. Okay, what color is this stupid thing? Blue. Blue. I don't like that blue. More colors. Darken that up. Okay, blue. Green.
Yo, I didn't know Rick was on it.
How do you get up to that for? Maybe it's hard.
Well, that's not helpful. How do I add another one?
I asked her, is that right?
Okay. Add. Highlighter. Green. Okay. Draw. Highlighter. Blue. More colors. A little bit less blue. There we go. Okay.
It was okay. It was not bad. Like, I did good on this.
It's like 100%. Like any other day. It was 100, straight 100. And then 4%.
I can change pen colors? Oh my god! Okay, that's good. So exciting.
1, 2, 3, 4.
Okay, I don't know where everyone is, but it is now 20 after. So we're gonna start. Let's make sure I'm still recording. Hello. Okay, I don't know what I just did. Zed. Oh, God. Ah! Okay, what is happening? Why? Restart program. Okay. Well, I guess it's not starting right this second because we're restarting the program because it's having a little hissy fit. Okay. Super fun. That's okay, it's restarting. Good times. It'll give everyone a chance to get back here. Okay. Okay, and I don't want that one. Got it. Alrighty. So, we had 2 examples back here where we added, why does it do that? Where we added calcium and one of the ions that was the dissolved substance was calcium. Yes? So those 2 substances, they have an ion in common. Yes? And in our next example, we had some hydroxide and we had some hydroxide. And so the calcium hydroxide and the sodium hydroxide have an ion in common. Yes? And in both those instances, when we add a substance that has an ion in common, what happened to the solubility? It decreased. Now, why? We can change the concentration of ions in many different ways. This one has a name. Why does it get a name? And the other, like when we add HCl and it decreases the hydroxide, we don't give that process a name. We just say, okay, we decrease the hydroxide, so it shifts to the right. These 2, where we add an ion in common, that is known as the common ion effect. Yeah, the common ion effect. And the common ion effect means you add an ion in common and it decreases the solubility. Now, do you need to You guys are 5 minutes late back from break, you know that. We've started already. And you missed learning about the common ion effect. Too bad. So sad. So sorry. Okay. So moving right along, you can always, if you want to, decrease hydroxide by adding an acid. Because, of course, the hydroxide will react with hydrogen and will produce water. Now, there's another one that is not as intuitive, and that is we can also decrease carbonate by adding an acid. Now, let's see why that works. Okay? So, we had our hydroxide. We had our carbonate. Now, when we put hydrogen together with carbonate, we get H2CO3. Okay? And if you have done biology, you might know what the other thing is that can happen to H2CO3. It can become H2O and CO2. Yeah, so this is a buffer, but in your blood it is a buffer because where is carbon dioxide going to go? It goes out your lungs, but at your cells, it's just going to be in the blood. Yes, it doesn't go anywhere until it gets to the lungs. These are in open beakers. Yes? So where is the carbon dioxide gas going to go? It is going to escape. Okay, and these are actually equilibria. Whoops. Okay. But since the CO2 gas escapes, what happens to the concentration of CO2? Yeah, concentration of CO2 decreases, which shifts this equilibrium here to the right. And if that's the case, what's happening to the concentration of H2CO3? Is decreasing. And therefore, what happens to this equilibrium? It shifts to the right. So anytime you want to decrease carbonate concentration, you can add an acid. You'll get bubbles coming out, CO2 will come out, and you'll get water. So it is, you can write this as a two-step procedure, where first you have the hydrogen and the carbonate coming together to form carbonic acid, and then separating into H2O and CO2. Or your other option would be just to say that we have (2H plus CO3, 2 minus gives H2O plus CO2. Yes? And you can almost draw that as a single way arrow because as long as the carbon dioxide keeps escaping, it's going to go to completion. Okay? Okay, so now here is another example. We have MgCO3 solid. How can we increase the solubility? Tell your partner. What's one way we can do it? We can add an acid. (2H plus CO3, 2 minus, goes to H2O plus CO2. If you prefer to do it the two-step, that's totally fine. Okay, therefore the concentration of CO3, 2 minus, decreases. Therefore we shift to the right. Therefore more MgCO3 dissolves. Is there any other way that we can increase the solubility? We could increase the temperature, okay? That increases solubility. What happens to KSP? KSP increases. What happened to KSP when we added an acid? KSP stayed the same. Any other way we could increase the solubility of Mg2CO3? We just did temperature. We could add hydroxide. Yeah, we could add NaOH. Tell your partner how that makes it more soluble. What happens if we add NaOH? What does it do? It reacts with Mg2 plus. So what we get is we get Mg2 plus aqueous plus 2OH minus aqueous gives Mg OH 2 solid. Therefore, concentration of Mg 2 plus decreases. Therefore, we shift right. Okay, very nice. And now we're just going to try a couple of typical questions you might see with something like this. In which of the following solutions, they are all 100 milliliters, and then we have all the same concentrations. We have 0.1, 0.1, 0.1 molar calcium nitrate, sodium chloride, and HCl. In which will you be able to dissolve the greatest, and I forgot one, there's one down at the bottom, 0.1 molar NaOH. Which one will you be able to dissolve the greatest mass of calcium hydroxide? And then once you've figured that out, figure out which one you'll be able to dissolve the least amount of sodium hydroxide. How about A? Is that an increased solubility or a decreased solubility? Decreased, because we have this going up and then this going to the side. Yes? How about NaCl? No change. How about HCl?
Yes.
Yeah, we have a decrease in OH. And so we have an increased solubility. And how about NaOH? We have a decreased solubility. So who is the most soluble? Calcium hydroxide will be the most soluble in HCl. Excellent. Okay, and we're going to skip that one where I said is it the least soluble, because that gets complicated because the OH is a squared term.
What? So what is it though?
I believe because it is a squared term, so we have KSP is equal to, it has a larger change, and these are going to be small numbers to start with, right? So it's going to make the right-hand number smaller. What? I don't know. My brain hurts. I need lunch. It's lunchtime. I'm not getting lunch. This computer is messing with my head. Can we think about that another time? I think I might have covered it in the other class, if you want to check that out. Can we just think about that another time? Because you don't really need to know it right now. Okay? In which of the following solutions is calcium fluoride least soluble? And now we have different concentrations of things, right? Which one?
If I were to guess,
D. Why D?
it has the most concentration.
It has the highest concentration, so it's going to shift it the most to the left. It has the highest concentration of a common ion. Therefore, it is shifted the most to the left. Shifted most to the left, therefore, least soluble. So the basic moral of the story here is that the degree to which an ion affects the solubility does depend upon its concentration. The higher the concentration, the more it will affect the solubility. And oh, aren't you guys lucky? We are going to talk about the common ion effect again. All the preceding examples are really just LeChatelier's principle in action. Yes, nothing more to them than that. One of these methods has a special name, and that special name is called the common ion effect. Why it gets its own special name, we don't know, but there we are. So what is the common ion effect? It is when we add a soluble compound and what does that do? It decreases the solubility. And that's because the soluble compound has an ion in common. Ooh, that's not a good pen. That's a really bad pen. Let's not do that. It has an ion in common with the precipitate. Okay, so the soluble compound has an ion in compound with the precipitate. So let's say we are looking at, this is our ionic precipitate here. Have you ever worn those glasses that make it like upside down when you do things? Yeah, that's not, this isn't like that, but when you're used to a pen doing one thing and all of a sudden it does another, so when you're used to your pen writing rather than moving things around on the page and all of a sudden it's moving things around on the page, it messes with your brain. Like the cognitive dissonance is very jarring. So if you see me looking like this, it's not because I'm mad at you, I am just so like, yeah, it's driving me crazy. But anyway, hopefully I'll figure it out, or they'll get my other computer working. All right, so we have our ionic precipitate. We can decrease the solubility by adding either NaCl, right? Because we've got the Cl, which is in common with the AgCl, or we can add something with silver. Okay, so silver is in common with the other ion. And it doesn't have to be sodium chloride, it could be potassium chloride, any kind of chloride. Doesn't have to be silver nitrate, although it maybe does have to be because there aren't very many soluble silver compounds. Maybe silver acetate would be the only other one. Okay, so here we have all kinds of common ions with our chloride though.
Wait, so it has to be like a silver.
Either a silver. Okay, so here is our reaction of interest, yes? And in this case, I'm just showing you a bunch of things that have chloride in common. Yes? So if we added any one of sodium chloride, aluminum chloride, potassium chloride, calcium chloride, any one of these things will decrease the solubility of AgCl. Yes? Now, the reason I chose to show a lot of examples with the chloride is because, like I said, there's not very many silver compounds that are soluble. So if you added silver bromide, that would not do very much because silver bromide does not dissolve. Silver carbonate does not dissolve to any great extent. So really, if you wanted to make it less soluble, I'd be much more tempted to add chloride than silver because it's just easier and less expensive. Okay. Does changing an ion concentration, so if we change the ion concentration, does that have an effect on the solubility? Yes. So changing an ion concentration changes the solubility. Yes. Does changing the concentration of an ion have an effect on the solubility product constant? No. Things that do not change the solubility of the salt. Let's imagine you have a saturated solution of the salt. So we have a saturated solution of a salt. Will adding, if you add more, sorry, I'm not reading this correctly. Will more salt dissolve if you add more water? Yes. Has that changed the solubility?
No. This all really like a problem.
Yes. And the reason it has not changed the solubility of the salt is, yes, you have more water. Yes, you have more water. And you have more dissolved salt. Yes? And what is solubility again? Solubility is the concentration of a saturated solution. Yes? So, my original concentration, saturated, is X salt over moles of salt over Y liters of solution. Yes? So we have a ratio there. My new saturated concentration, I have more moles of salt, but I also have more liters of solution. So what can I say about the ratio? The ratio is the same. You don't even need to get that complicated about it. You can just be like, hey, a saturated solution is a saturated solution. And like Tony said, solubility is a property. And it's an intensive property. It does not depend on how much there is, right? You cannot make something more soluble by adding more water, right? Because it's how much will dissolve in a given volume. You've changed the volume, so it's just different. All right, what will happen? Will more salt dissolve if you add more solid salt? You've got your saturated solution of salt. Will more salt dissolve? No. It is already saturated. You'll just have a bigger pile of solid. And then I think I just ramble on a little bit here, saying basically what we said there. Does adding more water affect the KSP value? No. Only temperature affects KSP. Blah, blah, blah. Blah, blah, blah. You have a bigger surface area if you add more solid, but that increases both the forward and the reverse rates. Yes? And now we're at exercises. Oh, look at that. What time is this class over? 12:05. We have 15 minutes left. I would love to stop now, but I got here with my other block yesterday. Oh. So... Why? Because we've been behind for a while because you guys ask more questions, which is fine. I don't mind that, but I wanted to use today to get caught up a little bit. Okay, let us take a quick look at then. Do we remember? Oh, let's see. This is page 48. Do you remember how to do dilutions? No. Okay, let's go to page 48. Has that been tilted all class and you guys haven't said anything? Oh my goodness. There we go. Is that better? Oh, okay. Goodness gracious. All right, so diluting just involves adding water, right? Does the number of moles change? No. So if you can find the moles that you had originally, and are you guys good at finding moles given a volume and a molarity? Yeah. Then you can just say, I found my moles, I'm going to divide it by my new volume. Yes? So in this example, we have these two things, each of which represents a mole. Yes? So we now have, and if this is 1 liter, then we have 2 moles in 1 liter. So that's our concentration. Now, if we add another liter of water, right, now we still have our 2 moles, 1, 2, but now it is in a volume of 2 liters, right? So now, if you can find the moles, you can then find the new concentration. You just divide by your new volume. Yes? Okay. And you get 1 mole per liter. And basically, you should, over time, kind of get the idea that if you double the volume, the concentration halves. What kind of relationship is that? That's an inverse relation. So there's an inverse relation between concentration and volume of solution. So basically, to do this kind of dilution, you find the moles of the solute. And then you divide by the new larger volume. Do we need to do any examples of that, or are we okay? Is that okay? Okay. Dilutions 2. So this is where you have a concentrated stock solution. Have you guys heard of a stock solution? Okay. A stock solution has a relatively high concentration.
Oh, is it like a one way of like a stock? Like diluted?
Yes. Yep. So for example, I need to, at some point, make some more 0.1 molar HCl because we use it in these little bottles all the time. But we have some 1 molar HCl back there, and I'm going to dilute my 1 molar HCl to 0.1 molar. Now, knowing that it's an inverse, by what factor am I changing my concentration if I go from 1 molar to 0.1 molar? 10 times. So by how much should I dilute it? 10 times. So if I started with 1 liter, I would want to make 10 liters, which sounds like an awful lot. I would probably not do that. I would probably want to make 1 liter. So I would take 100 milliliters of my stock and then dilute it to a final volume of 1 liter. Okay? But again, what it comes down to is you find the moles of the solute, and then you calculate what volume you need. Okay? And we're actually going to skip ahead. Skippity skip. No, we're not. We're going to do this. Here we go. So we want to make 2 liters. Of our solution at a 2 molar concentration. Okay? And our stock solution is an 8 molar concentration. Okay, so we're starting at 8. We're going to 2. This is going to be a 1 in 4. Yes, because it got 4 times less concentrated. So we're going to want to quadruple the volume. But it won't always be beautiful like that. So let's do the actual math behind it. So here we have our stock solution where we have, here's our stock solution where we have 8 moles. Eight moles in 1 liter. So that's 8 moles per liter. What do we want to have? What we want to have is we want to have 2 liters, right? So here's our 2 liters. And we want it to be 2 moles per liter. So this here is 1 liter, yes? So I want to have 2 moles in that 1 liter. And here's another 1 liter. So I want to have 2 moles in that 1 liter. So how many moles do I need altogether? I need 1, 2, 3, 4 moles. So what you would do in an instant like this is you would say, I know that I want 2 moles per liter of 2 liters of 2 moles per liter. And that means I need 4 moles. How much stock solution contains 4 moles? Half a liter contains 4 moles. Yeah? So now if you wanted to do the calculation for step 2, you could say, I need to get 4 moles, and I am starting with 8 moles per liter, so I need to put my 8 moles on the bottom and my liters on the top, and that gives me 0.5 liters. Okay? That's the basis behind all these doodads. Doodads, that's what I'm saying, sure. That's the basis behind all dilutions. However, so to do a dilution calculation, you can always just find the moles. That's going to be step 1. And then you'll just, if you're asked to find volume, find the volume. If you're asked to find molarity, find the molarity. Step 1 is always just find moles. I got my first co-op job by being able to do that. Because I could do that because I'd just done a summer of, what was it called? It was like a quantitative chem lab course, right? So there was a lot of dilutions. Or you can use the dilution formula. I've honestly never loved the dilution formula. I tend to put the wrong thing in the wrong place, but everyone else in the world seems to love it. So here we are. M1V1 equals M2V2. Okay? M1 and V1, usually you would use those for the initial molarity and volume. M2V2 for the final concentration or molarity and volume. You will also see this as C1 V1 equals C2 V2, where C stands for the concentration. Okay? My favorite method, I love the noon method, which is if I'm trying to find my new concentration, I take my old concentration, and do you remember how if I quadruple the volume, my concentration gets quartered? So if I start with 1 liter and then I finish with 4 liters, and I call that, this is called the dilution factor. And it just makes sense to me, but if you don't love it, don't use it. Use M1V1. This is the dilution factor. So you can do these calculations many ways. We don't have time to do that. So for homework for the weekend, number 1, you're going to study for your quiz. But number 2, you are also going to do la 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 la. Oh yeah, right, not that one. You guys did 3.2a and 3.2b, right? Yes? Okay. So you guys are going to do the exercises on page 41. Page 41 plus study for your quiz. So that's just a little bit to remind you of what happened today. And then you're going to study for your quiz, which is section 3.1. Let me know if you want the page references from Hebden. I can probably sort them out. Or you can just look them up because you have a table of contents. Yes? Yes. Hi.
I'm not quite understanding this one. Isn't that AG and CO will combine together and precipitate?
They will, but the concentrations when you, like, in the instant before they precipitate, they're going to be 0.1 molar.
So
if you can imagine time slowing down, and you're like, and they're like in there, and they're like, I'm 0.1 molar, and then they go boom. Yeah?
Okay. So
Yeah.
it will be precipitated.
Yeah, it will precipitate, yes.
Okay.
Yes, yes.
So if it's on the borderline,
Yeah.
it will precipitate.
Yeah.
Okay.
Yep, yep.
Thank you so much.
Hi.
Question, like it's all about this.
Uh-huh.
In here you said it's not dissolved more, right?
Yep.
But here it's isn't more.
Well, you said, what if the solubility were 100? Here you said, what if the solubility were 1? Here you said, what if the solubility were 100? That's making up numbers. I made up one number. I made up a different number.
So
I'm not
solubility-
actually saying that this will change. That number actually cannot change. How much will dissolve
yeah.
maximum cannot change unless you change the temperature.
Oh, but what if like we add more solid? Will it change like
No.
those two?
No,
Oh,
because it's already full.
I see.
Right,
So
saturated
the
is full.
solubility it's
Yeah.
constant.
Yeah. Well, the solubility, you can change it, like if you change these concentrations, right? Because then
Yeah.
they're not going to be in proportion to one another anymore. Yeah.
Oh, I see.
Yeah, yeah?
I see.
Yeah. Okie dokie?
Yeah.
Okay.
Okay, thank you.
Is everything with it on the classroom notebook?
Huh? Yeah, this is all on the classroom notebook. Same as usual, just my tools are not working as they should.
Monday is going to be amazing. I have 2 tests and a quiz.
Bye. I have had a couple people in that situation ask if they can quiz on Wednesday, and I was fine with that, so up to you.
We shall see.